If your printed circuit board keeps failing EMC testing even though it passes the design rule checks, there are at least 5 reasons why this could be happening. I'm Kirsch Mackey, an electrical and electronics engineering design consultant, and in this video, I'll be covering the top 5 reasons why your board might be failing EMC. Okay, mistake number 5, simulating your design too late. People, if they simulate at all, will simulate at the end of routing the PCB. This is a no. By the time you're doing this, you've already routed your vias, your traces, your PCB stack up. You've done all that work and it becomes expensive to fix any problems that come up in the simulation results. What you want to do instead is this. Start with the schematic. I like to simulate the PCB stack up, the materials and transmission lines along with SPICE and IBIS models in a sandbox-like environment. And I use the SIGRT-X Aurora topology workbench to do this. It lets me change all of those so that I can see what the results are at the receiver. Once I get the results, I put those into the constraint manager. Then I'm ready to start routing. Once I'm routing, I then simulate again section by section so that by the time I'm done with the PCB layout and simulate a third time at the end, I know I've hit all of my targets. This adds maybe 10 to 30 hours total on your design process, which is more time, I get it. However, the alternative is you getting a board that is failing EMC and do respins that may run you tens of thousands of dollars. That's mistake number 5. The next 4 are mistakes that engineers think they've already solved. Mistake number 4. Poor differential pair via symmetry. Differential pairs need to be balanced throughout the entire routing of the differential pair, even through the different layers of the PCB. When the vias on a differential pair have different anti-pads, different entry points into the inner layers of the PCB, different spacing, asymmetric ground return via placement, it's going to cause a mismatch in the signals between the two differential pairs. The phase mismatch creates common mode voltage and therefore common mode noise and EMI. So what's the fix? The fix is to keep your differential pair vias symmetric. Keep the same anti-pad geometry, maybe even combine them if possible. Use equidistant spacing and have your ground return vias placed at the same angles on both sides of the pair. This keeps the electromagnetic field equally coupled across both legs of the diff pair. If you're using Allegro X PCB layout, via symmetry is built into the routing tools already. So you don't have to calculate return path via spacing manually. It does it automatically. Okay, so mistake number 3, ignoring via stubs. A via that has signal traces going from layer 1 to layer 3 on a 12-layer PCB still has the rest of the via that's going through to the 12th layer of that board. That unused remaining barrel of the via is a via stub, and at high frequencies it's going to resonate and absorb signals. So what's the fix? The fix is to use back drilling to get rid of the unneeded via barrel, or to use blind and buried vias that don't create extra via stubs in the first place. But a key thing, you should pick your via structure based on the rise time of the signal going through those traces and the via, not just the PCB layer stack up count. The faster the edge of the signal, the shorter the stub you can use. Mistake number 2. Routing through different layers without proper return path control. When a signal changes through different layers on a PCB, the return current needs a low impedance path. If it doesn't have that path, the electromagnetic field spreads out, searching for some return ground. That increases loop area, it worsens the inductance by making it larger, and therefore the impedance gets bigger. Impedance times the currents going through the PCB produce a voltage, and those voltages that are unwanted create that EMI. So what's the fix? The fix is to place an adjacent ground via right next to any via transition you make on the PCB. NVIDIA's Jetson AGX Orin carrier PCB does this perfectly. Every signal via transition has a ground via right next to it, which keeps the EM wave from spreading to other conductive structures. At gigahertz speeds, placing a return path via will cause problems. Now, finally, mistake number 1. Trusting length matching to fix everything. Length matching handles timing and skew. That's all it does. It doesn't fix impedance discontinuities, broken return paths, bad terminations, or crosstalk. Equal copper length doesn't mean equal electrical behavior. So what's the fix? The fix is to treat length matching as one tool, not the whole toolbox. Check your impedance continuity, manage your return paths, get your terminations right, and verify that your differential pairs are balanced. Length matching done in isolation will not save your board from EMC testing. Passing the design rule check is a starting point, not the finish line. The EMC test chamber and the receiver pins on your chips care about the electromagnetic waves, not the PCB design constraints. Manage the electromagnetic waves and fields, and the rest of the board will take care of itself.